The final talk in this session will be on capturing types, and it's being given by Aleksander.
Oops. No. Okay, good. Hello everyone. Thank you for the introduction. I'm Aleksander Boruch-Gruszecki. I will be presenting capturing types, which is joint work with Martin Odersky, Edward Lee, Ondřej Lhoták, and Jonathan Brachthäuser. And we will be talking about two things today: a foundational calculus for tracking capabilities in types, and a surface language, a Scala extension actually, which uses capabilities to unify effects and resources and has a particularly strong focus on usability. And this presentation is roughly split too much. So, at the risk of stating the obvious, effect and resource ownership systems are both very significant areas. And as we have seen, we are sort of thinking about how to progress from what is already there. It's really no exaggeration to claim there were hundreds of papers in both areas, and yet, compared to the academic interest, industry adoption is somewhat lacking. So, yes, I mean, things like Rust ownership or Haskell monads are definitely very important, but really there could be so much more, and the benefits are there because both traditions allow checking important program properties. And if we have this hypothesis that if we find a way to reason about effects and resources which minimizes the adoption and migration costs as much as possible, we will make it easier for developers to adopt the approach. So let's see how we propose to do that. We adopt the object capability take on effects, which is that if we have an effectful operation, then it can only be accessed through some special capability object. So a function that wants to do something effectful must take a capability as an argument. And in our Scala implementation, this appears similar to classical effects. So the following two signatures for us are actually equivalent. We treat a direct effect annotation the same as an implicit parameter, and Scala finds implicit arguments automatically based on their type. So that means that capabilities can be passed around with zero syntactic ceremony. Now, the thing with classical effect systems is that they aren't really like usual types. So if f1 calls a chain of functions which ends in fn, then the effects of f1 include the effects of all the functions in this call graph. And that means that when typing, we need to do something special when dealing with a dynamic call graph. And these call graphs are actually very common, because if a function takes another function or an object as an argument and uses this argument, it has a dynamic call graph. So one example is the map function on list over here. So with classical effects, we must introduce an effect parameter, here that's the E, and then we must thread this parameter through the signature. Now, there are approaches which hide these parameters with syntactic sugar, but those parameters do tend to still show up in error messages and more complicated signatures. And in contrast with our capability-based approach, map can have the exact same signature it has in current Scala. So let me explain how to think about these types. With classical effect systems, function types track the so-called latent effect of calling the function. And the effect of calling map depends on its argument. So we must resort to introducing an effect parameter. So the signature of map must say something like this. Map takes an argument whose latent effect is E for any E, and the effect of map itself is E. Whereas with capabilities, we have a different mindset. We say that having an object means being able to use it by default. So what this means for map is that map can just use its argument. I mean, in a sense, of course, right? We call map, we give it a closure, so it gets a permission to use this closure. And in turn, that means that there is no need to really add anything to the existing signature of map. I mean, the caveat is that we add a type for pure functions. And the way we see it, there are two particular advantages to a capability-based effect system. First is that we get effect polymorphism for free. The two signatures that we can see express exactly the same information, the same, But with capability-based effects, map retains its current signature. And more importantly, there is a shift in thinking, because the entire system is built on the assumption that having an object means being able to use it by default. So the signatures focus on where objects go and much less on what objects are used. And in the common case where a definition takes an argument just to use it, no additional ceremony is necessary. I don't need to put anything in the signature to be able to use an argument that I already asked for. Okay, so let's talk about resources now. Here we see a program which processes the elements of some list. The list is X's and it gets mapped over with F. And F throws an exception if the element is too large. Now this is a well-behaved program, so the call to map is wrapped in a try. Now, it looks like Java code, but actually this is expressed in our Scala extension. There are capabilities behind the scenes. Throwing requires a capability, and we ensure all exceptions are caught. So if we remove some syntactic sugar, we see the try block introduces a can throw capability, which is captured by the closure passed to map, so that it can be later passed to F. And each can throw capability has a limited lifetime, which makes it a resource. It cannot be used after the try block is left and the handler for the exception is gone. Now, so far so good. Access to this capability is well scoped. However, in this snippet, we return an iterator from the try block and not a list. And in Scala, the map method on iterator is lazy, so the result retains the can throw capability, and using the returned iterator may result in an unhandled exception. And our implementation will statically rule out this example. And the core reason why it can do so is that we track in the types of objects what capabilities the objects may capture. Concretely, we introduce capturing types. And such a type comprises a regular type and a capture set, which describes what capabilities are retainable by inhabitants of the overall type. Now, statically, from the perspective of types, a capability is a reference whose type has a non-empty capture set. So, in a sense, we posit that every capability is derived from another capability, and that's cyclic. So to break the cycle, we add an exception, the root capability cap, from which all others are derived. So what we have here is a type systematic account of the object capability model and, importantly, its concept of capability derivation. Because you see, an object which captures a capability is itself a capability, according to how we think. So object capabilities are naturally organized into a hierarchy, and that hierarchy tells us what capabilities can do. So here is an example. We have a snippet with a main method which receives fs, a capability to access the file system. The first step of main is to instantiate the logger class, passing it fs as a constructor argument so that the created object can actually log messages. Now, logger is just a normal class, but this instance of logger is also a capability to log messages. The next step of main is to create a lazy list of integers. This lazy list logs some debug info while computing its elements, which makes it a capability as well. And the important idea here is that if an object wants to log messages, it does not get fs. It only gets log, which means it can only indirectly access the file system through the logger interface. Now, that's just a common sense way of structuring object-oriented code, but with object capabilities, it's also a way of controlling and mediating what effects code can perform, right? So what this example shows is that we have 4 capabilities here, and the types of capabilities not only describe that they are capabilities, they also concisely tell us how the capabilities are derived and what authority to perform effects they have. And this notion is deeply embedded into our approach. We have subcapturing, a relationship between capture sets. Subcapturing integrates capability derivation with the subset relation and is used to define subtyping between capturing types. So given fs and log from the previous snippet, we have that empty set subcaptures log, which subcaptures fs, which in turn subcaptures cap. Which finally brings us to our core formalism, CC sub box, also called capture calculus. It's a minimal extension to systemf sub. Besides capturing types, its key features include variable-dependent types, subtyping, and universal type polymorphism. And parts in gray show adjustments compared to systemf sub, which we made only to account for capture sets. So one of our goals was to make the capture calculus as simple as possible, but not any simpler than that. And in a sense, I mean, only time will tell if this is a very fundamental system or not. But as you can see, our system makes just a few strategic adjustments to systemf sub and fits on a single A4 page with some room to spare. And you may be wondering, why add universal type polymorphism to a foundational system? And the reason why is that there is actually some subtlety to doing so. So here is our example. We have this head application function. It takes a list of x's and returns a closure which takes a procedure and runs it on the head element of the list. Now the question is, what should be the capture set of the returned closure? It closes over HD, which might be a capability, but it's also a local variable, so it can't go into the type. Now, calling this closure might use HD. So at the very least, it seems reasonable that the capture set should be non-empty. So as a first approximation, we could say the closure could capture anything, right? As an approximation, that will do for now. And what happens if you work this out is that you will see that you actually need one extra capture set on the list. And that's a bit annoying, right? The list type now suddenly needs capture sets, and we still need to make the signature more precise, right? Maybe a bit like this. We need to thread C everywhere. So now it is precise. It barely fits on the slide, and it's not very pleasant to look at. And so we decided to explore an alternative in our system. And this alternative has roots in contextual model type theory. Briefly, we shift where capture sets appear. So we say that list doesn't get a capture set since its elements are in a polymorphic context. Instead, the capture set appears when the element is out of the polymorphic context and where it might be used, on the capture set of the procedure. And formally, this occurs by a boxing construct similar to CMTT. Now, this has a number of advantages. It's an interesting option where if a capability is not used, it does not need to count as captured, right? So a list holds capabilities, yes, but it will not use them. And what we have is a principled way of excluding such capabilities from the capture set of a list. And we found out that it just works well in practice. So what we did to evaluate how lightweight our annotations are is that we migrated parts of the Scala collection library to use our capture checking extension. And as you can see, there are barely any adjustments to the API of the list. Most list methods are like the map example. They take a closure to use it and just discard it. So their signatures get to stay exactly the same. They are on the happy path. And there are only two places that changed. Methods which take an iterable once as an argument, they need to put a hat on that type. And that's because iterable once might be computing its elements on the fly, and it might be using captured capabilities to do so. Now, in comparison, the iterator class requires a few more annotations since iterators are lazy and there are more cases where capabilities may be captured. Still, as we can see, the burden really is not too high and it's what you would expect. In the end, in such a system, the signatures need to show where capture of capabilities may occur. And since we have variable-dependent types, we can just use the parameter name to describe what gets captured. Okay, so let's start wrapping things up. What we also have in the paper is a classical proof of soundness. Perhaps more interestingly, we show that even though we shift where capabilities appear, we can still predict what capabilities are used based on capture sets. So that's our version of an effect safety theorem, since effects can only happen when capabilities are accessed. And we also have an extension to demonstrate that we can ensure capabilities are well scoped. Okay, so it's one of these slides. So we've seen just the tip of the iceberg today. We have discussed something like the origin point for a much broader project. literally in a week, I'll be defending a thesis which discusses the formal foundations in more details, and there's other things. There is an algorithmic capture calculus, a safe concurrency extension, a low-level concurrency library, and more than that. So if you are interested, you can find links and references on my homepage. Google refuses to index it, but I added a link to the description of the talk. Okay, so I'm almost out of time. So thank you, and happy to take questions.
All right, we have a few minutes for questions. All the way over there.
Thanks. This is very interesting work. Have you thought about developing some kind of formal result to show that this is as expressive as some equivalent system that just uses conventional effect typing?
I think you asked me this question before, didn't you?
I asked you that at your Uppsala talk, yes.
A year ago.
This is a different system.
This is a different system, but I mean, it's a different system. This one focuses more on subtyping, right? It has subcapturing, but it's also for the purposes of that question, it's very similar. I think that for the most part, we are basically as expressive. There might be, if we did add capture set polymorphism, then I think that it should be, I mean, a parametric capture set polymorphism, right? So if we had capture parameters, then I think we should be exactly as expressive. But I guess the way to do it would be to encode an effect system into this and see what happens, right?
Try it.
If I get the time.
Hi, so this is very nice work. One question I had was, you have a sophisticated subtyping relation, and it's with these variables showing up in the types. Your type system is a little bit dependent as well. How hard is it to implement an algorithmic version of this?
So the person who is most involved with the algorithmic implementation is Martin. There is also Wichenshu. I don't think I think it's basically as hard as you would expect. There are some difficulties, right? I mean, there are some difficulties, right? But I don't think it was that much of an issue. But still, I think you should talk to, okay, maybe.
It helps that Scala is based on the dot calculus, which already has these types. So we know how to have a part-dependent text system.
Okay.
We already have the foundations, but of course there's a lot more to add.
Okay, and does your implementation make use of paths and the captures?
Right now, no, only variables, but there are experimental work to extend it to paths, but it's not yet in the merged implementation.
Okay, thanks.
We have time for one more question.
Thank you. Very nice talk. You said early on that the compiler can infer the captures. And I wonder whether this is a good thing, because the whole point of object capabilities and capabilities is that you should be aware of them and you should stay within bounds. So if the compiler infers them, where do the guarantees and the safety come?
So at a point where we want to restrict where capabilities go, we can just add an explicit type annotation, right? And that type annotation will be inspected and respected by the compiler. And otherwise, for usability purposes, we really do need capture set inference. We really, I mean, we don't want, I mean, it's the same argument as for having type inference. Like we just don't want to add a type to every local binding. So if we want to restrict where capabilities go, we use an explicit type.
And nothing gets added then?
Yes.
All right, let's thank the speaker again.